Hello and welcome to the lecture on Introduction to Beamforming. So why should we care about beamforming? It turns out beamforming allows us to focus the ultrasound waves to form a coherent beam. So if you have a transducer with a large number of array elements, they can work together to form a single composite beam. Beamforming also enables the array to be sensitive to signal emanating from certain specific directions. So essentially, beamforming is a spatial filtering technique. For example, let's say you have people talking in the room. If you would like only to hear the signal from the speaker but not the chatter from the surrounding people, is it possible? Yes, it can be done by beamforming, which is also extensively applied in audio signal processing. Turns out radar, sonar, wireless technologies all employ beamforming, which is an important aspect of ultrasound imaging as well. So now beamforming allows better discrimination of signal of interest because it is a spatial filtering techniques. It can help us reduce artifacts. It improves the target SNR because it can help suppress the noise, and there is a property called dynamic focusing which we will be discussing later. It enables us to maintain focus across a larger depth. So the depth of focus is increased by beamforming, and thus overall beamforming helps improve image quality. So if you recall, the ultrasound beam can be broadly divided into two zones, the Fresnel zone, so Fresnel zone which is in the near field, and the Fraunhofer zone which is in the far field. And if you remember that if a transducer array is firing like this, then if this is the direction of the axis, then this we call as Z. And then there are two other directions, elevational direction and the lateral direction. So the resolution is relevant to all these three directions. Now let's talk about ultrasound beam focusing. So if you remember, if you have an extended aperture piston transducer, for example, even though you have not applied any geometrical focusing or a lens, there is a natural focus at a distance of d square by 4 lambda. We discussed this in a previous class. Now for a single element transducer, if you want to create a focused transducer, the only way is either to have a curved geometry or a concave geometry for the transducer, or to use a lens, right? However, for these transducers, once you put the lens or once you assign the geometry, then the focal length is fixed and it depends primarily on the geometry. So here is a picture where a concave aperture transducer is firing, and as you can see, it is focusing in this spatial region. Now if we look at the cross sectional beam profile, it will have a main lobe and side lobes. So this is the beam is actually symmetric, so half of the beam cross section is shown in this image. You have the main lobe here and these are the side lobes. Now these side lobes appear at certain angles. The main lobe is where the signal is the maximum, and that is why this is a normalized plot. So this is 0 dB where the signal is maximum, and the signal of the side lobes drops down. However, these side lobes are present and they will create artifacts in images. So you will recall that the main lobe width actually determines the lateral resolution of imaging, while the side lobe level relative to the main lobe level determines the contrast resolution. So now if we have a way of controlling our main lobe width, side lobe level, etc. using beamforming, it will help us improve our imaging. Anyhow, let's continue. So let's discuss transducer arrays. So here is a schematic of a transducer, and you have these crystal elements in gray. The spacing in white, which is called the kerf, is the insulation layer in between the transducers to prevent them from getting shorted, and the element to element distance is called pitch. And then we also discussed linear, curvilinear and phased arrays, which we will discuss in further detail in this and subsequent lectures. So typically the number of elements in an array are in the power of 2, so 32, 64, 128 or 256, which allows for some efficiency in terms of hardware. Now when these individual elements fire, they create a spherical wave as we discussed in an earlier lecture, but we can electronically scan the array to obtain B mode images. So, when we look at signal emanating from a large number of elements such as 32, 64 or 256 elements, we can use the principle of superposition to get the spatial pressure distribution. Essentially, when we take signals from all these array elements, there is constructive and destructive interference at different spatial locations, and the resultant of that gives us the beam. So, here is an image which shows the resultant signal. So, this is the resultant summation signal, and here are two sine waves or sinusoidal waves that are in phase. As you can see, they are in phase, they reach maxima and minima together, and when summed they sum coherently. However, here these two signals are out of phase, so when you sum them up you get 0, right. So, areas in which you have no beam energy, in those areas the signal sums up destructively, and the areas in which you have maximum beam energy, there is constructive interference largely. Now, if you recall the Huygens principle that we discussed, so here is a plane wavefront and here is a slit. So, now this slit acts as its own source and gives out spherical waves which are shown here. If we have an extended source, then we can consider it as being composed of several elements, and then the signal coming out from these several elements actually interferes to give us the beam. Now, let us look at this carefully. If you look in this zone, right, if you look carefully, it almost appears like a plane wave, right, the wavefront is plane. So, if we fire all the transducers together, we get an approximate plane wave, as we can see from this Huygens principle demonstration. But what if we would like to focus? So, essentially we want a directed wave, not a plane wave. We can change the focal length by adjusting the time of firing or by adding delays. Now, how is that? So, let us see the schematic. You have these array elements, these are array elements, and they are firing. Now, if they all were to fire together, and let us say they are firing in a tissue medium, the speed of sound is approximately similar in different spatial locations in this tissue medium. Let us assume a homogeneous tissue. So, now the element in the center is located closest to the focus. So, the signal from this element will reach first. However, signal from the furthest element will reach last. So, when you take those signals, so let us say this is the signal from the first, this is the signal from the second, and so on and so forth. When you try to sum them up, they will not sum up constructively, because there is a phase difference. Why is there a phase difference? Because there is a path difference associated with different lengths. So, as you can see, we can use Pythagoras theorem, and we can see that this hypotenuse is the longest distance that the ultrasound signal has to travel, right. So, now if we want to focus at the point, the necessary condition is that all the beams or all the signals should arrive in phase and sum up constructively to give the maximum signal here. And for that to happen, we would have to make them all arrive in phase, but the difference in path length creates a problem here. So, to compensate for the path length, we can apply delays. So, what is the extra path length that the signal coming from this furthest element has to cover, right. So, this is the signal coming from the central element and this is the path length. If we draw an arc, this is the extra path length that has to be covered by the signal coming from this peripheral element, right. And so, this path length y, right, has to be covered, and this can be calculated by geometry what this y is, right. Now, to cover y, the time taken will be y by c, where c is the speed of sound in the medium, in this case tissue, right. So, in this way, if I give a 0 delay to the center element, that means it fires fast, I can give sequentially increasing delays and the maximum delay will be y by c. So, in this way I can compute the delays, right. So, one way of visualizing it is here is that let us say I fire the element in the center first, after some time I fire the two elements which are located nearby, and after some more time I fire the elements on the extreme, and let us assume this as being the like increasing time. axis, right. So if I apply this spherical delay profile, it turns out that I will get focusing at this point. So another thing is, now because this delay profile is not fixed, I can change the delay profile, I can make the focus longer or also shorter, right. So if I have a profile like this, as you can see here, then the focus is longer, the focal length is longer, and if I have a more extreme delay profile, I can have a shorter focus. So this is the flexibility of array transducers. It is not a fixed focus, but we can vary the focus within certain limitations, right. There are some assumptions here. So it is not something that you can arbitrarily do, but within a certain range you can vary the focus. Okay. So now this focusing allows us to improve our lateral resolution, right. But what about elevational resolution, right. So we had discussed that there is another axis called the elevational axis, and ultrasound beam has a certain thickness to it. So the elevational resolution is also important. We would like the elevational focus to be tight. For elevational focus, what we do is we apply a lens. Now typically the lens will have a fixed focus. So you cannot have focus at multiple depths by using a lens, but if you have what is called a 2D array or 1.5D array, these are two different types of arrays. So in 2D arrays you have a matrix of elements, right, and you would probably have almost same order of number of elements in both directions, right. So in this 2D array you can apply delay profiles in this way, right, delay profiles in this way, meaning fire the center element first and fire the elements on the extreme the last. So this is one way of providing delay. You can also add a delay like this, right. So this will enable you to focus in both directions. So both the lateral direction as well as the azimuthal direction. Now it turns out this is a big advantage, but 2D arrays require complicated electronic circuits which are difficult to achieve, at least for traditional systems, not higher end systems. So there is a compromise which is a 1.5D array. In a 1.5D array you have a large number of elements in one dimension, but relatively smaller number of elements in another dimension. So one example could be 128 elements in one dimension, but say only 8 or 16 elements in the other direction. So you have some capability of providing delay profile like this and focusing in the azimuthal direction as well, but not as well as in the lateral direction. But nonetheless these 1.5D arrays are used more frequently than 2D arrays, and this is a trade off between the ability to do focusing in both directions very well versus not being able to focus in the azimuth direction except for a fixed focus with a lens. So moving on, now let us talk about something called apodization. So apodization literally means foot shaping, or you can think about it as footprint shaping, right. So first let us make an important observation. I have not done the derivation for this, but for now let us take this and remember this. This is a very important point, that if you have a transducer and you look at the focal point, right. So here the pressure field is actually the Fourier transform of the source velocity. So what do I mean by source velocity? This is my source, this is my transducer. For now let us just think of this as a single element transducer. So now this will be oscillating, right, in this manner, and it will be oscillating with a certain velocity u. So this velocity profile is going to match the geometrical profile of the transducer, right. So whatever is the shape of the aperture, the profile of the velocity will also look similar, right. So now if there is a Fourier transform relationship between the field profile and the transducer aperture, so if I have like a rectangular aperture like this, if I take a Fourier transform, what is the Fourier transform of a rect function? We know that it is a sinc function, and what is problematic about a sinc function? Sinc function has a main lobe which is good, but it also has side lobes which will be problematic from the point of view of imaging. So, what if we could shape the aperture in such a way that we would reduce the side lobes? It will be impossible to completely eliminate the side lobes given the finite aperture of our transducer. Given the finite aperture, we cannot focus just to a point, but it will be diffraction limited focusing, right. So, if there was a way to actually shape the geometry of this aperture in such a way that it would only have a main lobe and reduce side lobes, that would be beneficial. But if this is a single element transducer, right, I cannot really change the profile, right. All the entire aperture is actually oscillating in a very similar manner, and so the profile will be rectangular. I cannot do anything to change it. But if I have an array, I can actually apply what is called apodization, and using this Fourier transform relationship, I can reduce the side lobes. So, for that what I need is I need a smoother velocity profile. I think in signal processing you may have studied about windowing, right, windowing a signal using a smooth window such as a Hamming window, Hanning window, Chebyshev window, etc., to reduce the side lobes, right. So, same thing we can do here, we need a smoother source velocity profile to reduce the side lobes. How will we do that? So, because here we have an array, right, and we discussed how we can give different delays to the different array elements to focus. But have you considered that apart from a different delay, we can also give different voltages to these transducer elements, right. So, if we provide the highest voltage to the center element here, and then we have a progressively decreasing voltages on either sides. So, essentially we provide a voltage profile, right, something like this. So, then when we take the Fourier transform, because of smoothing of the aperture, because there is no abrupt change in the aperture now, unlike the rectangular profile which it was earlier, you will get no side lobes. Well, this is an idealization, of course there will be some side lobes, but they will be really reduced in the focal zone, right. So, if you have a smoother function, there are lower side lobes. So, if you remember, if you have a Gaussian function and you take the Fourier transform of the Gaussian function, the resulting Fourier transform also has a Gaussian profile, right. Now, it would be impossible to apply Gaussian here because Gaussian requires what you call as infinite support. If you truncate a Gaussian, right, it is not Gaussian anymore, right. Gaussian function goes all the way to infinity on both sides, but this is a good analogy to understand that if you have a smooth profile and you take the Fourier transform, you will again get a smooth profile and the side lobes will be reduced. So, here is an example, here is a transducer and this is the focal plane, and at this point I want to look at the profile. So, I am taking this cut, right. So, now if this is approximately rectangular transducer, right. So, here I am showing a circular piston, but I think it would be more appropriate to consider rectangular transducer in the context of this example. So, if you have a rectangular window, right, then the Fourier transform is like a sinc, and as you can see there are many side lobes here, right, and the side lobes are fairly high. So, they would start at roughly around 10 dB relative to the main lobe somewhere here, and then you have all these side lobes that are present, right. Now, here in the figure I have a circular function, right. So, the Fourier transform of a rectangular function is a sinc and of a circular function is a jinc, that is also somewhat similar function to a sinc. So, even in that case you would see lot of side lobes. Now, when I apply what is called a hand window, right. So, I have applied a hand window. So, essentially this is now an array transducer, right. I have an array transducer and I have applied a profile of amplitude in such a way that the center element gets the maximum amplitude and the side elements get lower amplitudes. Then what I will see is I will see the Fourier transform here, where still you see some side lobes, but they are very significantly reduced compared to the first example. Another thing what you will notice, and I will show you here, this is the main lobe, right? This is the main lobe, and now let us look at the main lobe here. So, if you compare, you will see the main lobe has broadened a little bit, right? And engineering is all about trade-offs. So, now the main lobe is broader, but the side lobes are reduced. So, we have made a trade-off where main lobe is broadened a little bit. So, we will have some loss of lateral resolution, but we will gain in contrast resolution because the side lobes are suppressed. So, now let us say we have an array. So, how do we fire the array, right? There are different ways of firing the array, right? One way is what is used in traditional linear array imaging, in which we group a few elements and we fire, right? So, we had an example in a prior lecture where we said that let us say we have a 128 element array and we group 32 elements and we fire, then we shift by one element, we fire again, and we said the number of fires will be 128, which is the total number of elements in the array, minus the number of grouped elements, which is 32, plus 1. So, 128 minus 32 plus 1 would be the number of times we would have to fire to create an image. So, that is shown here. So, let us consider this is the array, right, and initially I group a few elements and fire my beam. So, this is my beam here which I am firing. Then the receive signal, so let us assume that this is diffuse scattering happening here from tissue. So, the signal will go all the way like this, okay, and it will be captured by different elements, not only by the elements which have sent the signal. Now, I can also apply an apodization on receive, right, because when we perform imaging, it is an interplay between the transmit beam, right, and the receive beam, okay. So, both will together determine the resolution and imaging performance of pulse echo imaging. So, here we first fire few elements, then we shift, we fire again, we receive, we fire again and we receive, and as we do this, we are able to combine all the signals and get this image, right. So, this is called focus transmission mode. It is used very frequently with linear array imaging. So, few elements are grouped and fired to get an A line, and we can use delays to create a focused beam and therefore improve lateral resolution. So, as you can see here, this is where the focus is. So, this is the point where, or this is the line along which you will have the best lateral resolution. Now, another way of creating images is what you call ultra fast imaging or plane wave imaging. Now, it turns out in this case, if depth of imaging is d, right, speed of sound is c, then the time taken to reach and come back is going to be 2d by c, right. So, for firing once and receiving, the time taken is going to be 2d by c. Now, if I am firing multiple times, like I said in the previous example, I am firing 128 minus 32 plus 1 times, right. So, this is the total time taken to create a single image. Now, if you can calculate the time taken to create a single image and you take the reciprocal of that, it gives you the frame rate, which is basically number of frames per second. Typically, for linear array imaging, we can get 50 to 80 frames per second, right. Why? Because you have to fire multiple times to get one image. But now, what if we were to fire all the transducers together to create an approximate plane wavefront, as we saw in the earlier example, that when all the transducers fire together, approximately plane wavefront is created, because all elements create their own spherical wavefronts and they interfere and they create an approximate plane wave. Now, the advantage is even if I have 128 transducers, all of them are firing together. So, if I want to image at a depth of d and the speed of sound is c, then the time taken to create one image is only 2d by c, right. So, this is very fast. Now, because this is an unfocused way of transmission, there will be poor lateral resolution. So, it is very fast, that means high temporal resolution. You can distinguish between two events in time because you are capturing very fast frames, right. I think you must have all seen ultra fast imaging cameras, high frame rate cameras, where you can see events which are not otherwise visible if you take high frame rate images and then you slow down the images and play a video, right. So, similarly here we can capture events that are very fast and that are not otherwise visible using these high frame rates. However, the lateral resolution is poor. So, is there something we can do to fix that? And luckily there is a way. There is a technique called angular compounding which you can do. For this you need to be able to steer the beam, therefore you should use phased arrays, right, and you can fire the beam at angles. So, this is like one angle, this is the second angle, and firing right in front is the third angle, and then you can combine the signals. So, this is called compounding because you are combining these three group of signals. When we do that, we improve the axial resolution, right, and we also improve the signal to noise ratio. So, now the total time taken is going to be 2d by c times n, where n is the number of compoundings you are performing. So, if you are compounding 3 firings, then it will be 3. If you want to do like 7, it will be 7, right. So, this is a trade off where you are reducing the frame rate a little bit, but you are improving the lateral resolution, and this compounding actually also reduces the speckle. So, that is another advantage of using this spatial compounding. This is a spatial compounding and also known as angular compounding because the beam is fired at some angles. Now, this image I have shown here, this angle looks extreme, it looks something like firing at 30 degrees or something, but it turns out that in practice we use small angles, something like 5 degrees or 7 degrees. That is more practical and that also allows us to get a good lateral resolution. So, here are some salient features. The advantage of plane wave imaging is its temporal resolution. If you want to capture a fast phenomena, you want to use plane wave imaging. Now, some fast phenomena that happen in the body could be, for example, propagating of shear waves. When Professor Carla Macardo Shekhar teaches the topic of elastography, she will talk about shear wave elastography, in which we image the propagation of shear waves in the body, and there the waves are travelling at speeds ranging from 1 meter per second to 10 meter per second, and to be able to capture them you need to have high frame rate. So, plane wave imaging is the only possible strategy there. Now, this improved temporal resolution comes at a cost of poorer lateral resolution, but you can have reduced motion artifacts. So, for example, if you have moving targets, you will have reduced motion artifacts, there will be no blurring induced by the motion, that is because of the high frame rate and good temporal resolution. You can recover imaging quality to an extent by coherent compounding, and when applied to Doppler imaging, there is a technique called ultra fast Doppler. Plane wave transmissions are also called ultra fast imaging because of the capability to get high frame rates. So, depending on the depth of imaging, you can also attain 10,000 frames per second. That is why the name ultra fast. So, when you perform Doppler imaging with this ultra fast approach, it gives you unprecedented sensitivity, 25 to 50 times more sensitive than traditional Doppler, enables you to look at low blood flows which are not otherwise detected by traditional Doppler. So, that is where the applications of plane wave imaging are, but it is not yet applied very widely, it is only used for specific applications in the clinic, because of the complexity of implementation and higher data volumes. I gave you some examples. People use it for elastography, ultra-fast Doppler, perfusion imaging, etc. But there is a complexity of implementation. The hardware requirements are more prohibitive, as well as the data collected is very high because of the high frame rate, and therefore these are the limitations, hopefully, which will be overcome in the future with advancing technology. Now let us discuss beamforming on receive. So, like we discussed, we can apply delays in transmit and focus at a particular depth, but even when the signal is coming back from a point scatterer. So, let us say you have fired the signal and it is arriving in phase at this point scatterer. Now, the point scatterer generates a spherical wavefront and the signal is not going to arrive at all the transducers at the same time. So, now the idea is to sum up the signal, but these signals are not in phase, because again the distance is different. So, again we would like to apply delays and bring the signals in phase, right. So, that process is called receive beamforming. We will discuss more about this in future classes, but the main point here is that beamforming needs to be performed not only on transmit, but also on receive. So, let us discuss the technique of delay and sum beamforming. So, the lack of coherence in the received signal will affect the image formed, because the signals will not sum up coherently. Beamforming allows this incoherent signals to be recombined to get its exact spatial distribution of a target. Only when all the signals arrive at the same time or are detected at the same time, only then we are able to make an image of the point scatterer, otherwise the scatterer will be extended. So, lastly, let us discuss focusing on receive. So, it turns out when you send a delayed profile wave and make the signals arrive in phase at a certain point, once the signal is scattered from the scatterer, again what you see is that the signals will arrive at different times at the various transducer elements. So, the signals will not arrive in phase. The closest transducer element will get the signal first, and the other transducers will get the signal after a certain delay. So, this delay occurs because of the location of the scatterer relative to the transducer elements. So, what we can do is, we can correct for this delay and we can make all the signals align, and then when we sum up the signals, we will get a strong signal from these scatterers. So, for that reason, this is called focusing on receive. Focusing on receive allows us to bring these signals in the same phase and we make them sum up constructively. So, like we discussed, focusing can be done both on transmit and on receive. So, more on this later. But let us conclude this lecture for now. So, in this lecture we discussed beamforming techniques for linear and phased array transducers. We discussed various transmission modes, especially focused and plane wave, and we also discussed how we can focus on transmit and receive, and we will continue this discussion on beamforming in the next lecture.